So he shall be talking on Clark measures on symmetric domains. With this, I would like to invite him for the talk, and I also request all the participants to mute their microphone. Over to you, Professor Calzi.
Okay, thank you, and thank you for inviting me, and good afternoon to everyone. The topic I will consider today concerns Clark measures on some particular sets, which are symmetric domains. I will try to stay as simple as possible because intuition of the symmetric domains is not as immediate. And I will start with the classical situation. So Clark measures on the unit disk in C. Then I will consider some properties of symmetric domains and focus on some examples. And then I will tell you something about some possible extensions of this theory to this more general context. So in order to introduce the Clark measures, the classical situation of the unit disk, it is necessary to recall the Rees-Herglotz representation theorem, which may be stated in two equivalent ways. The first one says that if you take a positive harmonic function on the unit disk, then this may be represented in a unique way as the Poisson integral of some positive Radon measure, or if you prefer a positive Borel measure, on the torus, finite Borel measure, where the Poisson integral is given by this kernel. Why does this happen? Because if you take f and you dilate it, so you consider f of rho alpha or rho z, or rho smaller than 1, and then you get a harmonic function which is continuous, well, it is harmonic on a neighborhood of the closed unit disk. And so the reproducing properties of the Poisson integral tells you that this function, this dilated function, may be reconstructed as the Poisson integral of this restriction of the dilated function to the torus. And then you pass to the limit, and the fact that the limit exists is related to the fact that all these measures here, these dilated functions, are positive and all have the same mass, which is the value of f at 0. Because of the properties of the Poisson integral. If you take z equal to 0, you get 1. And so they stay in a relative compact set for the weak convergence or vague convergence, and the limit exists. The other formulations concern holomorphic functions. And so if you take a holomorphic function in D with a positive real part, you apply this result here to the positive real part, and then you use an integral kernel, which is some holomorphic kernel, which gives the Poisson kernel as a real part. And this is the Herglotz kernel. You have to add an imaginary constant because these integrals are always real at the origin. But besides that, this is the complete analog. This is the same result in a sense. So why is this result useful? Because we are taking a holomorphic function from the unit disk into itself, and an alpha in the torus. And sorry, there is no pluriharmonic measure, sorry. So there is a unique positive measure, mu alpha, on the torus, so that its Poisson integral is equal to this function, which is harmonic because it is the real part of a holomorphic function, and it is also positive because of this equality. Notice that this is nothing but the Poisson kernel composed with phi in one variable and evaluated at alpha in the other one. So it is essentially the composition of the Poisson kernel with phi, in a sense. And these measures, mu alpha, are the Clark measures associated with the phi. And I will denote with mu alpha s, the singular part, with respect to the canonical measure on the torus, the Begg measure, normalized Begg measure. And here are some elementary properties, but not all elementary, of these measures. The first one is that since these measures are positive, And as I told you before, the Poisson integral at the origin is simply the mass of the measure. The mass of the measure is simply the value of this function at the origin. So it is known. You may also find the absolutely continuous part of this measure with respect to Lebesgue measure. And it is simply the boundary values of this function, radial limits of this function where they exist. And concerning the singular part, in general, it is more difficult to describe, but at least you can say that it is concentrated in the set where the radial limit exists and takes the value alpha. And so in particular, if you take different values of alpha, you get mutually singular measures. And then there is the Aleksandrov disintegration theorem, which states that if you consider the mu alpha as functionals...
Can you go back to the previous thing? This where, okay. So mu alpha is constructed on phi1 inverse of alpha.
See, this is the set where the radial limit of phi exists and it's equal to alpha. Is a subset of the torus.
Okay.
You take the radial limits. So an alpha prime belongs to this set if phi of rho alpha prime has a limit for rho tending to 1, and this limit is alpha alpha. This set is a Borel set, but in general, it may be a very rough set.
Okay, thank you.
Okay, and concerning the disintegration theorem, if you consider the mu alpha as continuous linear functionals on the space of continuous function on the torus, you can take the integral with respect to Lebesgue measure, and the integral of these functionals are Lebesgue measure, considered as a continuous linear functional on a continuous function with convex support. And then, by the theory of integrals of positive measure, you know that if you take any function which is integrable with respect to Lebesgue measure, then it is integrable with respect to mu alpha for almost every alpha, and the integrals of this function with respect to mu alpha are an integrable function of alpha, whose integral is the same as the original integral of the function. So this equality holds not only as linear functionals on continuous functions, but also on L1 of Lebesgue measure.
What is the definition of inner function here?
Linear function?
Inner function.
Okay. It is below. So a function such as this one here, so from the unit disk into itself, is called inner if its radial limits are unimodular almost everywhere.
Okay.
So this means that this object here is 0, because you have 0 here. And so the inner function are precisely the function for which the Clark measures are singular. So if you take an inner function, this is actually a disintegration, meaning that these measures here are concentrated on these joint sets. And but this is only a remark. There is not much more. Instead, from this formula, you may, for instance, deduce that if you take an inner function which maps the origin into itself, then the boundary values of this function preserve the Lebesgue measure. And another result concerns the fact that if you take a function not necessarily inner, which preserves the origin, then you can describe the Fourier coefficients of the measures mu alpha by means of this formula, where in principle you can compute these objects here, even if you don't know what the mu alpha looks like, because this refers only to phi. And of course, you can also get the Fourier coefficients with the zeta to the k without the conjugation, because the measures are positive, and so you can take the conjugation outside and you get all Fourier coefficients. Okay. And these measures were actually introduced by Clark in order to study some contraction operators. And this is the link between these two settings, these of Clark measures and the contraction I'm going to define in a moment. The link is this operator, and which is the normalized Cauchy transform, because this object here is the Cauchy integral of the function f with respect to this measure mu alpha. This is the Cauchy kernel. And this object here, at least when phi maps the origin into itself, is the reciprocal of the Cauchy transform of mu alpha. So this is a normalization of the Cauchy transform with respect to the Cauchy transform of mu alpha. And this is called the normalized Cauchy transform. And this operator is contractive, and its kernel is the orthogonal complement, or in L2 of mu alpha, of the closure of holomorphic polynomials. And
this contraction is a strict contraction, or is it norm of C alpha f is less than equal to norm of it? Is it a strict contraction or only just contraction?
It may be, it may not be. The fact is that one, in fact, would like to consider some other spaces related to the hard disk space here, which depend on phi, and this becomes a partial isometry onto those space, which contractively embed in H2. And if phi is inner, this map is actually an isometry, because the kernel is 0, and this is an isometry.
Okay.
It's not onto, its image is the orthogonal complement of this object here, which is a closed subspace of H2, because phi is unimodular on the boundary, so it acts as an isometry in the hard disk space. You can think the hard disk space as its boundary values, and this boundary values is the closure of polynomials in L2 of Lebesgue measure. So in L2 of Lebesgue measure on the torus, phi acts as an isometry, because it is multiplication by a function which has unimodular values. And so it may be a very small space if you consider the zero function. You simply get something which is not very interesting, and you may get well, you get a whole space in that case. But if you consider, it depends on the function you consider. It may be strict contraction. It may be almost an isometry. It may also be a unitary operator. It depends on the function phi. And the original situation was that in which phi was inner, and well, for simplicity, consider the case in which maps the origin into itself. Then this mapping, as I said before, is an isometry of L2 of mu alpha onto this space, which is a model space for some particular kind of contractions. And the inverse of this mapping is explicit, and it is simply given by taking the radial limits. So if you take a function here in this model space, its radial limit exists mu alpha almost everywhere, and this is quite interesting. And these radial limits are, in fact, the element of L2 mu alpha, whose C alpha is the original function. And this is a result of Poltoraski. And the result by Clark is that this normalized Cauchy transform acts as an intertwining operator between the shift, which is multiplication by Z, on L2 of mu alpha, And this is a unitary operator, a diagonal operator in some sense, and some unitary operator on this model space, which is a rank 1 perturbation of the compressed shift. What does it mean? You take the shift on this space here. The problem is that this space is not closed under multiplication by z. So you multiply by z, and then you apply the orthogonal projection onto this space. The orthogonal projection from the Hardy space onto this closed subspace. And you get this compressed shift, which is almost an isometry. And it only lacks some rank 1 operator. And then all the rank 1 perturbations of this compressed shift, which are unitary operators, may be represented in this way. And so there is a natural connection between these Clark measures and this unitary operator. The problem is that for the topic I'm going to describe in more variables, this link is very unclear. So this is the original formulation, but then the theory of Clark measures developed more also in the direction of of studies functions on the unit disk. And here are some examples. The first is the case of phi is rational and inner function. And this means that phi is a finite Blaschke product. So it is an object of this form. It is a product of a unimodular factor, monomial, and a product of these objects here, which are simply biholomorphisms of the unit disk with the different zeros. And so you get the rational unit functions are on this form, and the corresponding Clark measure may be described completely in this way. So you take the values of the elements of the torus where phi is equal to alpha. Notice that phi is defined on a neighborhood of the closed unit disk, so there is no need to consider radial limits. And you take the alpha double prime, whose value is alpha, and you take the Dirac delta at this point with this coefficient. And in general, one may say that H2 of mu alpha is equal to F2 of mu alpha, which means that holomorphic polynomials are dense in L2 of mu alpha, if and only if the function phi is extremal in the closed unit ball of H infinity. That is the space of bounded holomorphic function with the supreme unknown. And I would like to highlight that this equality here depends only on the properties of phi and not on alpha. And this is not the same for the case I'm going to describe later. And so let us pass to some information concerning bounded symmetric domains. So the definition in general is this one. You take a convex, circular, so invariant under the action of the torus, bounded open set, which has this property. Every element of D is the unique fixed point of an involutive biholomorphism of D. And this biholomorphism is then unique, and the biholomorphisms of D act transitively on D, but it is another topic. It is important to know that the group of linear biholomorphisms of D does not act transitively on D, but acts transitively on the set of extremal points of D, which I will denote by BD, and is often called the Shilov boundary. This is also the smallest closed set of the closure of D for which the maximum modulus principle holds for a function which extends by continuity. And so we may consider this is a compact group with a natural topology, and so we may consider the normalized K-invariant measure on the Shilov boundary. This will be the replacement for the torus and the Begg measure thereof. And in fact, it is the back measure on K on BD, which is an analytic manifold. And here are some examples. The first one is the unit ball of Cn. This is bounded symmetric domain. In this case, K is equal to the unitary group, and this shadow boundary is simply the whole boundary. If you consider the unit polydisc in Cn, then in this case, K is maybe described as a product of the n torus, which acts by component-wise multiplication, and the group of permutations on n elements, which simply permute the variables. And the shadow boundary is the n torus. Notice that this is strictly smaller than the whole boundary. And then there is another example, the space, the unit ball for the space of n by n square matrices with the operatorial norm. And in this case, one may describe K as this product of the torus acting by multiplication, so diagonal elements, and this special unitary group squared, which acts by composition on the left and on the right. And the shadow boundary is the unitary group. So these are the examples that I will carry on in the discussion. In order to have some analog of the Poisson kernel, I need to briefly discuss the Hardy spaces on this setting. So in this case, I use the Smirnov definition of Hardy space, and so require these to be the space of holomorphic function on D, whose dilets are uniformly bounded in L2 of the shadow boundary with respect to the canonical measure that I defined before. This is a possible analog of the Hardy space on the unit disk. In the case of the unit ball, this is quite familiar. And this is a Hilbert space. This mapping, which takes F to the radial limits, which exist almost everywhere, is an isometry of H2 into a closed subspace of L2 of the canonical measure on the shadow boundary. And one may show that point evaluations are continuous linear functionals on H2, which is the same as saying that there is a unique CZ in H2 for which point evaluation may be represented as scalar product against CZ. This is the replacement for the Cauchy kernel, because the Cauchy kernel would be the object that you would use to reconstruct the function from its boundary data. Here you use this object, which will be called the Cauchy-Zygor kernel. In this, in the example I considered before, in the unit ball, you get this object here, which is somewhat similar to the usual Cauchy kernel, apart from this power n here. In the polydisc, you get the product of Cauchy kernels in each variable, which is what you normally use in the elementary part of several complex variables. And for a unit ball of Mn, you get this object here, which is some sort of analog of the Cauchy kernel. Simply you have to use the determinant because this object here is a matrix. This is the star means the conjugate, the Hermitian transpose. And then we may define the Cauchy-Zygor kernel, as I said. These are the functions which represents point evaluations as a scalar product against these functions. And this function happens to be quite well behaved because its reciprocal squared is essentially holomorphic polynomials. In fact, in these cases, it's reciprocal without the square is a polynomial. Here is a polynomial, this is a polynomial, and this is a polynomial. But in general, one has to take the square, no problem. And this means that since this polynomial does not vanish on the product of D and its closure, this function C extends to a sexually holomorphic function on a neighborhood of this object here. In particular, it is continuous. And so we may define the Poisson-Zygor kernel. This also often considered as the Poisson kernel, but in order to avoid possible confusion with the Poisson kernel for a harmonic function, which is a completely different thing, I'm going to call it the Poisson-Zygor kernel. And this is defined this way. This is a fancy definition, and the reason why it works is that in the classical one-variable situation, this is exactly the Poisson kernel I described before in terms of the Cauchy kernel. And it has some similar properties because it is a continuous function, it is bounded, it gives rise to probability measures on the boundary, the Schiller boundary, and it has some approximate identity properties, meaning that if you take the dilates of this Poisson integral, these dilates considered as measures on the Schiller boundary converge to the measure mu. Vague convergence is the same as weak convergence, so convergence against continuous functions on the Schiller boundary. And this is a class of measures that I'm going to consider. These are called the pluriharmonic measures. Well, a pluriharmonic function on D is a function which is harmonic on every complex line. And this is the same as saying that it is locally the real part of a holomorphic function. But since this domain is convex, this means that these are globally the real part of some holomorphic functions. And this is an extension of this concept to measures on the Schiller boundary related to the action of this Poisson-Zygor integral. So a measure is said to be pluriharmonic if its Poisson-Zygor integral is pluriharmonic, which is the same as saying that it is a real part of some analog of the Herglitz integral. This object here is always a holomorphic function, but it is in general not related to this object here, unless the measure is pluriharmonic. And this is also equivalent to the fact that mu is in the vague or weak closure of the space of pluriharmonic polynomials, so real parts of holomorphic polynomials. And this is also equivalent to saying that it is orthogonal to every polynomial, which is orthogonal to every pluriharmonic polynomial, so a biorthogonality principle. And the nice result, which extends the Ries-Haglotz representation theorem in this context, says that if you take a positive pluriharmonic function on D, then it is the Poisson-Zygor integral of a unique positive pluriharmonic measure. The proof is the same, essentially. And this is a bijection between positive pluriharmonic functions and the positive pluriharmonic measures. And before passing to the theory of measures, I would like to say something about the theory of pluriharmonic measures in this context. So if you take a pluriharmonic measure and you consider this quotient of BD of the Schiller boundary by the action of the torus, which means that you put BD into the projective space, then you may consider the canonical measure, which has some invariance properties with respect to another group. And you have this integration. So you may write mu as the integral of these measures mu psi, each of which is supported on the torus in the direction psi. Well, you can take the complex line determined by psi. This complex line has an intersection with your domain D, which is a disk, because D is convex and circular, and this boundary is contained in the Schiller boundary, and it is in fact the section of the Schiller boundary with this line, and it is a torus. This is this object here. These measures are so supported on this tori, and so they are mutually singular, and this formula holds. And this, in fact, follows from this result here. So if you take the Poisson-Zygor integral of mu, and you consider it on the disk in the direction xi, and then this is the usual Poisson integral of mu xi. Where here I am assuming that the Shirov boundary has the elements of the Shirov boundary all have norm 1 or modulus 1 for simplicity. Otherwise, you have to replace 1 with the modulus of the elements of the Shirov boundary. And furthermore, if mu is positive, then these mu xi are uniquely determined by this relation. This relation happens for every xi. And this is a vaguely continuous family of measures. And I'm going to skip the proof. And a consequence of this result is that if you have a pluriharmonic measure on the Shirov boundary, and M is the dimension of the Shirov boundary, which I recall is an analytic submanifold and a real algebraic set, then mu is absolutely continuous with respect to the Hausdorff measure with dimension m-1, which does not mean that it has a density with respect to this measure, which is false, but it means that if you take a negligible set for this measure, then it is negligible also for mu. And so, well, this is a simple result because this measure is absolutely continuous with respect to this Hausdorff measure with dimension m-1. And so the only singularities can arise here, and there is only one dimension to allow for these singularities. This is simply a consistency result, which says that this relation here not only holds for the Poisson-Zygor kernel, but also for the Cauchy-Zygor kernel and the Cauchy kernel here. And as a consequence, one may extend the Poltoratsky distribution theorem, which describes the distribution of the values of the Cauchy transform for large values to the case of pluriharmonic measures. And for the time being, I'm going to skip this part. Maybe I return to it later. And I'm passing to Clark measures. So we may define Clark measure exactly as before. So we take a holomorphic function from our bounded symmetric domain to the unit disk, and you take a unimodular values in the torus, and then there is a unique positive pluriharmonic measure mu alpha on the Shirov boundary of D, for which the Poisson-Zygor kernel integral of mu alpha is equal to this function, which is both pluriharmonic because it is the real part of some holomorphic function, and positive. So we may apply the result by Koren and Kansky. And again, I'm describing as mu alpha S the singular part with respect to the canonical measure on the Shirov boundary. As before, we know that the total mass of the mu alpha, which is nothing but the integral of the mu alpha, is simply the value of 0 of this function here. Particularly, these are probability measures if phi maps the origin into itself. Again, the absolutely continuous part of this mu alpha is explicit. It is given by the boundary values of this function here, radial boundary values. And again, these singular parts are concentrated on the set where the radial boundary values exist and take the value alpha. So again, these measures are singular for different alphas. So these are completely analogous to the one-dimensional situation. We have also the Aleksandrov disintegration theorem. Here, the integral of the mu alpha with respect to the Berg measure is the canonical measure of the Shirov boundary. If phi is inner, which as before means that the boundary values are unimodular almost everywhere, then this is in fact a disintegration because these are concentrated on these joint sets. And if in addition the function maps the origin to itself, then the boundary values of phi map the canonical measure on the Shirov boundary onto the Lebesgue measure on the torus, normalized Lebesgue measure. And we also have this analog of the computations for the Fourier coefficients. Of course, these are not Fourier coefficients unless we are in the unit D, in the unit polydisc. But this still describe our measure mu alpha, because you get the integral against all conjugate holomorphic polynomials, then by conjugation all holomorphic polynomials, and then all pluriharmonic polynomials by summation. And since the measure is orthogonal to the polynomials which are orthogonal to pluriharmonic polynomials, in principle, you know the integral against any polynomial, pluriharmonic or not. But in order to do so, you have to decompose the polynomial into its parts, which is not completely obvious. But in principle, this is a complete description of the measure mu alpha, even though rather implicit. And then we may define the normalized Cauchy transform exactly as before. We have the Cauchy-Zygor kernel. We may consider the integral of some function f with respect to mu alpha and normalize it by this function here, which again is the reciprocal of the Cauchy-Zygor kernel in the integral of mu alpha. This mapping is again contractive. It is in fact a partial isometry when phi is inner. It is no longer one-to-one when phi is inner in general. And again, its kernel is the orthogonal complement of H2, which is the closure of the space of holomorphic polynomials in L2. And here are some results on this normalized Cauchy transform. So if you take the unit ball, which is our first example, then one may show that any pluriharmonic measure on the Shilo boundary, which is singular with respect to the canonical measure, which is simply a Hausdorff measure on the boundary of U, then this measure is totally singular, which means that it is singular with respect to any probability measure which gives point evaluation on holomorphic polynomials. So integration, again, this measure is point evaluation at some given point, for instance, the origin. And for example, if Z is the origin, and this definition does not depend on Z, if the Z is the origin, then measures of this kind are simply any Cauchy integral on any equatorial circle in the unit ball, in the unit sphere. And so there are quite many such measures, so it is a very deep result. And as a consequence of this fact, one may show that if phi is inner, then mu alpha is totally singular, because we knew that it was pluriharmonic and singular. But in addition, we know that polynomials, holomorphic polynomials are dense in L2, or mu alpha. And this is known for inner function. I don't know if there is an analogous characterization of this equality in terms of extremal functions of the space of the unit ball in the space of bounded holomorphic function, and as in the case of the unit disk, because the tools that are available in the one-dimensional situation are not available in this case here, and this proof is completely different and quite more involved, even for inner functions. And concerning some examples, as we in the unit disk, I consider rational inner functions. There weren't quite many, but in this case, in general, there are more rational inner functions, but it depends on the shape of the domain. In the case of the unit ball, there are no rational inner functions. But for instance, in the unit polydisk, there are quite many, and they are fully described. So for rational inner functions, the Clark measures may be described explicitly. It is described in this way. So it is a measure which is supported in this set here. The closure of this set here is simply this set here. So if you represent phi as the quotient of two coprime holomorphic polynomials, P and Q, then say that phi is equal to alpha, means that P minus alpha Q is equal to 0. So essentially, you are considering measures which are supported in this set here, which is a real algebraic set in the Schirr boundary. And the density is a constant, which is explicit and depends only on the domain. And the gradient of phi, the modulus of the gradient of phi, which is a complete analog of what happened in the unit disk, where we had the Dirac deltas because m was 1. In this case, m is larger than 1. And this is a complete description of the Clark measures. In this case, what happens for the quality of H2 and L2? This is more tricky because already in the case of the unit polydisc, if you take a rational inner function, then polynomials, holomorphic polynomials are dense in L2 of mu alpha if and only if the closure of this set, which is this algebraic set here, does not contain any algebraic hypersurface, which in some sense does not depend on some variable. So it is defined by a polynomial which does not depend on some variable, which means that it is up to the permutation a torus times a hypersurface in the n-1 torus. So in particular, if phi doesn't depend on some variables, this happens always, because this object here does not depend on one variables at least. And so polynomials are never dense. But it may happen, for instance, in this case, that H2 is equal to L2, so polynomials are dense in L2 of mu alpha, or all alpha except a finite number, in this case 1. Because if you take alpha equals to -1 and you take the numerator minus alpha, the denominator, so plus the denominator, you get a function which is 2zz prime plus 2. And sorry, you get 2zz prime minus 2z minus 2z prime plus 2, which is a product of two functions which depend on one variable only. And so it contains two tori. This object here, the zero locus, contains two tori, and so this fails. And it is interesting to consider some very sketch of the proof in the case of the bidisk. The case of the polydisc is more technical, but the idea is the same. So, on the one hand, we may consider the case in which this object here, which is essentially the zero locus of P minus alpha Q, does not contain any horizontal or vertical torus. And so in this case, we may consider this polynomial here, which is 0, mu alpha almost everywhere, and decompose it as a polynomial which does not depend on z plus a remainder. And these polynomials are unique. So what happens is that Q1, this polynomial here, does not vanish on the closed unit disk. And the reason is that if you take a point in the unit disk and you assume that it vanishes, then this object here vanishes at 0 z prime, because if you take z equal to 0, this vanishes. And this means that the phi of 0 z prime is equal to alpha, which does not belong to the unit disk. And this is a contradiction, because our assumption is that phi maps the bounded symmetric domain into the unit disk, the polydisk into the unit disk. In the case of alpha prime in the boundary, this is slightly more tricky, because you have to consider some parts of phi in the boundary. But the point is that this object here, as quotient of these two polynomials on the boundary, is well defined. And it is well defined because of these two assumptions. Well, one of them, this one, is well defined as a rational function, and it is not constant, or again, because of this assumption. And so it is a rational inner function on the unit disk, And at the origin, it takes the value alpha, again, because of this property here. And this is, again, a contradiction, because it is an inner function, it is not constant, and so on. And so what do we get? We get that this sum here is 0, mu alpha almost everywhere. So we may write the conjugate of z as a holomorphic rational function, or mu alpha almost everywhere. And this rational function is defined on a neighborhood of the closed polydisc. So it may be uniformly approximated by polynomials, by holomorphic polynomials. And so you may approximate z bar on in L2 of mu alpha. So it belongs to H2 of mu alpha, in the same way you show that z bar prime belongs to H2 of mu alpha. And so by multiplication, these are bounded functions, you get that all polynomials belong to H2 of mu alpha, and then by density, H2 of mu alpha is equal to L2 of mu alpha. So this is a very explicit proof in some sense, because it essentially shows why this particular polynomials, particular simple polynomials, belong to H2 of mu alpha. The converse is, in a sense, simpler, but not that much. So, for instance, if you assume that this vertical torus is contained in the support of mu alpha, then, well, actually, one may do without this particular result, but it is easier in this way. What happens is that the gradient of phi is constant on this vertical torus, and because of the description, of mu alpha, so you get this as a density. You get that mu alpha is bounded from below by a constant times the Lebesgue measure on this vertical torus. And so, if you assume by contradiction that holomorphic polynomials are dense in L2, you know that z prime bar is the limit in L2 of a sequence of holomorphic polynomials. But then it is also a limit in L2 of this measure here, because this measure is smaller. And so this tells you that Pj alpha j of alpha prime dot, which is the holomorphic polynomials in the unit disk, converts in L2, so in Hardy space, to this function here, which is not the boundary values of the holomorphic function. And this is a contradiction. And this fact here, the fact that this in fact says that your measure mu alpha restricted to a vertical torus or a horizontal torus is in fact again a pluriharmonic measure. This is quite special of the polydisc, and it is moreover the multiple of Lebesgue measure of the torus. This is related to the part that I skipped, to this part here, which is an analog in the Pauli-Haperov plane of the representation theorem, but I'm not going to go into details. And so that's all I wanted to say. Thank you for your attention.
Professor, so I have a small question. Can you hear me?
Yeah.
Yeah, so I'm asking, like in the polydisc case, when you are looking at this inner function P and you are considering alpha plus P over alpha minus P, then you have a measure or the Herclose representation or Korani-Pukansky representation. And in that case, do you have any extra information about that measure? Because here we are considering some special kind of function with non-negative real part.
Are you asking if in the case of the polydisc, do we know the shape of mu alpha more precisely?
Yeah.
As rational inner functions?
Because in general, we know that the support, I mean, the Fourier coefficients are supported on the first quadrant and third quadrant, say in the bidisc case. So if we consider this special kind of Herclose function, do we have extra information on the Fourier coefficient?
Well, the Fourier coefficients may be reconstructed partially here, because if you take, well, taking a Fourier coefficient means that you take here, say in the bidisc, z to the k and z to the h, where h and k are integers, not necessarily positive.
Yeah.
Okay. So if one of the two is 0, then you are in this situation because you get a homogeneous holomorphic polynomial of some degree. And up to a conjugation, you can assume that the degree is positive because the measure is positive. And so you can describe the Fourier coefficients. If both h and k are non-zero, then your polynomial here is orthogonal to any pluriharmonic polynomials, which means that the corresponding Fourier coefficient is 0. When the polydisc is particularly simple because you know that all Fourier coefficients which are not in the two axes are 0, and the other one are described in this way, which is essentially the same that we saw in the. Did it happen? No. Great. Okay. Which is essentially this way here. Only you take one variable at a time. But besides that, it's the same. In the case of the polydisc, where you have this nice behavior of the monomials. If you take the unit ball, for instance, it is a mess because there are not even Fourier coefficients properly.
Right. Yeah.
And in fact, it is very, very difficult to provide examples of pluriharmonic measures in the case of the unit ball, of singular. For a long period of time, experts in the field believed that there were no singular pluriharmonic measures in the case of the ball. Then it was disproved by Aleksandrov, but no explicit examples are known of singular pluriharmonic measures in the ball. In the case of the polydisc, there are some examples, some non-trivial examples, for instance, because you have this description here, for instance. But one may provide more examples. In the case of the ball, there are no rational inner functions, so this gives no information in the case of the ball. I don't know
Also, So is there any parallel study? I mean, you are considering rational inner function, so is there any parallel study of inner function? Because as you said, in the ball case, we don't have rational inner functions, but we have inner functions. So is there any study of inner function in this setting?
In the case of the ball, there are a couple of papers by Dovtsov and Aleksandrov, where the case of these measures associated with inner functions, but sometimes even function which are not necessarily inner is studied. And besides the results that I showed, well, there is not much because well, there are some descriptions because the point is that there are two possible definitions, in some sense, of the analogs of the model spaces in several variables, because one may take the large model space, which is here, this object here. So you take an inner function, which again acts as an isometry on H2. And so this object here is a closed subspace. And if you take the orthogonal complement in H2, you get the large model space. And in this situation, for the case of the unit ball specifically, this mapping here is an isometry of L2 of mu alpha onto that large model space. And then Aleksandrov and Dovtsov considered the problem of which are the functions here which correspond to the function here for which f times mu alpha is pluriharmonic. So not only mu alpha should be pluriharmonic, but the measure with density f with respect to mu alpha should be pluriharmonic. And this is a smaller, let's say, model space. And they provided a characterization of this smaller space, which is essentially which is another characteristic. Well, this smaller model space is may be characterized in a way which, in the case of the unit disk, is the same, is the whole model space. So the model space may be characterized in two ways. The first one is as the orthogonal complement of that space, so of phi times H2, which is something. But it may be, in the unit disk, it may be also characterized as a space of functions in H2, F, which may be written as the conjugate of some G times Z times phi, where G is another function in H2. And this is because the orthogonal of H2 in L2 of the boundary is H2, the conjugate of H2 times Z. And this reflects two model spaces in this by this representation. In the case of the unit ball, this representation does not describe the whole, the big model space, but the smaller one, the one for which f times mu alpha in this representation by means of the normalized Cauchy transform is pluriharmonic. So it is a very, very, very smaller space. In particular, it means that if you take sectionally your function in the smaller model space, sectionally it belongs to the usual model space corresponding to the restriction of phi to your unit disk in the direction of some complex 9 passing through the Shilo boundary. I don't know if this section-wise definition describes a larger space or the smaller model space, but for instance, this is a property of these particular functions in the smaller space, which is not shared by the whole, the bigger model space. So in the case of the unit ball, there are a couple of papers that I'm aware of. There are some papers in the case of the polydisc, but they are mainly devoted to rational inner functions. And for more general domains, almost nothing. They're essentially what I told you, not much more, that I am aware of course.
And in the proof, are you using the structure of the rational linear functions somewhere?
Sorry, I didn't understand.
So I'm saying that in the polydisc case, this rational linear function, they have a special structure. Are you using
Yeah.
structure?
There is a structure. Well, there is a. They have a precise description because. Okay. The description by Rudin, I guess. They may be described explicitly as the quotient of.
P over P star, something like that.
Well, there is a complete description. I didn't use it, but other people used it. Well, the original results by all these people here used that description quite heavily. I didn't need the description, but it is useful nonetheless, because it allows you to construct examples, at least.
Yeah. Yes.
And there is also a description of rational linear functions besides polydiscs. For instance, in the case of the unit ball in the space of matrices, there is a corresponding description, but it is by Korani, I guess. But it is.
Yeah.
Sorry?
Korani and Bhagi.
Yeah, exactly.
Yeah.
And but it is not that precise as the one in the polydisc, because it tells you how these functions may be described, but it doesn't tell you when this description gives you a rational linear function. And it is not obvious how to construct the polynomials, which, well, if you take polynomials which are sufficiently well behaved, you construct examples, but there are other polynomials that you may suppose that do not give you rational linear function, but instead give you rational linear function. So if you consider only the polynomials that you would have liked to use, you may get fewer rational linear functions that than actually are there. Because the problem is that in more variables there may be some compensations in some sense, and it cannot be more specific without some text.
Are there any other questions, Mainak? Do you have?
No, I'm done. Thank you, sir.
Okay, so if not, let us thank the speaker for a nice talk. Okay. Thank you, Professor Calzi. So we'll end this meeting now. Okay.